This is Ishi from Microsoft AI for Good Research Lab. It's my great pleasure to present our project Automatic Lesion Detection and Segmentation in PSMA PET CT images using deep neural nets. This is a joint work with Ivan, Sarah, Anthony, Shen, Aman, and Huang. Prostate cancer is the second most diagnosed cancer type in men. Castration-resistant metastatic prostate cancer leads to the deaths of over 350,000 people globally every year. The PSMA PET imaging will significantly improve how prostate cancer is detected and treated. In the figure is an example where the cancer can be easily detected by the PET image. As a comparison, it is quite challenging to locate the cancer using CT image alone. To optimize the treatment, we need to know where the cancer is. For example, we would like to detect prostate cancer spread and also compute the total tumor volume. The very first step is always to do lesion detection. Unfortunately, right now, lesion annotation has to be done manually. As a result, it is labor-intensive and cannot be easily implemented in routine clinical practice. In this work, we aim to develop a convolutional neural net-based framework for lesion detection and segmentation of prostate cancer metastasis in PET CT images. We have over 500 whole-body PET CT images of patients with metastatic prostate cancer. The transaxial PET image size was 192 by 192 pixels, and the CT images were downsampled to the same size. In each image, up to 5 lesions were manually delineated by a physician, and the mean number of lesions per image was 2.23. Here is our model. We have 3 types of inputs. The first is a PET slice, second is a CT slice, and the third is the slice position. And then we concatenate all these 3 types of input together and fit it to a segmentation model. We also try to include not only the center slices, but also the neighboring slices. Hopefully, the neighboring slices will incorporate 3D contextual information that improve the model performance. 480 images were used for model training, 30 for model validation and selection, and 78 for model testing. The loss function is the dice coefficient. The architecture is the UNet with a ResNet34 backbone. The final model is the one with the minimum loss on the validation dataset. How we evaluate the model on the testing images? We evaluated the model from 2 aspects. The first is lesion-wise error measurement. We measure whether the lesion has been detected and also the lesion-wise IOU. For image-wise error measurements, we calculate the detected rate and also the image-wise IOU. Here's our result. The final model uses 9 slices include 8 neighboring slices. The model did a great job on majority of the testing images, except a few false positives. As shown on the image, these positives are quite close to the prostate and the bladder. And these are a few examples where the model missed the lesions. As you can see that these lesions are usually small, and then they either have a low SUVs or they are close to organs with high SUVs. There is one example where there are unusual high SUVs near the arm, and then the model gets confused. Here is the summary of the experiments to examine the power of incorporating more neighboring slices. As you can see on the 2 graphs, having neighboring slices definitely improve the model performance in terms of the lesion-wise or image-wise IOU, the lesion-wise or image-wise detecting rate. Having more neighboring slices does increase the image-wise IOU. However, it does not necessarily increase the lesion-wise IOUs nor the detected rates. So why? This is due to the nature of the loss function. Pixels from different lesions are treated equal. As a result, larger lesions are prioritized. The model is better at detecting medium or large size lesion. So here is the distribution of the volumes of missing lesions versus those have been detected. As you can see that more small lesions are missing. As a comparison, all the large lesions have been successfully detected by the model. To tackle this problem, we propose our own solution, that is to rebalance the loss contribution by the lesion volumes. After applying the rebalance loss, the model is able to detect more small lesions. We in addition evaluate the model performance in terms of the detected rate and the IOUs. By applying the rebalance laws, the image-wise and the lesion-wise mean detected rate increase, as well as the lesion-wise median IOU. However, the image-wise median IOU decreases because the model tends to have more false positives to be able to detect more small lesions. In summary, we developed a convolutional neural nets-based framework for lesion detection and segmentation of prostate cancer metastasis in PET-CT images. The final model achieved a median IOU of 0.28 and a mean detected rate of 77% averaged over all the testing lesions. We demonstrated the benefit of including neighboring slices as part of the input. Finally, we proposed laws that could improve the detection of small lesions. Here are all the references. Thanks for listening, and I would like to thank all of my partners.